So we should be good this time. We got audio going. All right. So are we ready for class? All right. So I just wanted to show the updated version of the flyer for the Codeathon that's going to be in April. Because one of my students in CISP 310 was actually on the planning committee of the Codeathon. So she was able to give me the updated version before it gets even circulated. So the first thing is there's a QR code. If you want to scan the QR code and then go to the link there, that's one way to do it. And you want to sign up before March 30th. So you got about 2 more weeks, to kind of think about it and see whether you want to sign up. You can always sign up and not go. Okay, that's the other way to look at it. Yeah, the sign up late, they may just kind of say, okay, sorry, there's a cutoff. So it's a little bit cute, okay, that they used. I think this is JavaScript can certainly do this. I'm not sure whether C can do it or not. I don't think so, because C requires a type before you can declare anything. So this is definitely JavaScript. So it's 8 to 5 at Sacramento City College at Sac City. I don't think the event or the competition itself is going to be 4 plus 5 or 9 hours. I think they have 1 hour or so at least for the opening and the closing, and rewarding awards and stuff like that. So there'll be prizes. There will be pizzas. It just says there will be pizzas. It doesn't say whether it's going to be enough or not. See, that's a very important qualifier. Okay, because all this says is there exists pizza. Yep. The yellow text. Okay. So the yellow text says return you plus your friends plus awesome time. So what you're going to get in return, I guess, you guys all will have an awesome time. All right. So the actual date of the event is April 6th. I think it's a Friday? Saturday? I cannot remember. But look it up, if it's a Saturday. Okay, so it's on a Saturday from 8 to 5. So just check out your calendar if you have time. Check it out. Okay. So the rest of this says calling all programmers, coders, developers, and scripters. Are you up for a challenge? Da 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 da. Okay. And this one is very different compared to the hackathon that I went to, because this one has no commercial sponsors. Because if they had commercial sponsors, you'll see their logos right here. It's like Google, Facebook, Lyft, Macy's, huh? Yep. But since there are no such logos, that means they did not get sponsored. Well, Los Rios, we are a part of Los Rios, so it's a Los Rios, sanctioned, or recognized event. And it's also ACM. Okay, so if you don't know what ACM is, go ahead and look it up. I believe it is acm.org. It's a professional organization for software people, computer science people, and so on. And we do have a local chapter of the Los Rios chapter of the ACM. Unfortunately, it is the home of that local chapter is over at Sac City. So ARC does not have its own local chapter. So if you want to join the local chapter and kind of check out what they do, you kind of have to go to Sac City, I suppose, for all the activities and whatnot. So anyway, think about it, and if you want to go, just go ahead and sign up. I got one student asking me about how do I prepare for something like that, and my answer was, well, get a good sleep the night before. That's kind of it, okay? Yeah, because you can try to study, all the algorithms, under the sun, and that's just going to overload your brain because you'll be spending so much time, trying to memorize all the code and all the different algorithms and whatnot, and there's no room left to actually think on the spot. Yes.
I think it'd be good to work on your own projects too. In the meantime, just try to find a project that has
Yeah.
a team and just work on it. That's pretty much what you'd be doing.
Yep. So there's the event, and it's also good to go, just kind of with a mindset of curiosity. It's like I just want to check it out, and see how I compare to the other contestants instead of saying, I'm gonna win. I need that $500 for my rent. Okay, so that may not be a very good mindset. Yeah, it's just that when you have that mindset and you do not end up actually winning the first prize, the $500. One, you'll be very disappointed. Two, you'll be kind of pissed at whoever actually won the prize, and then three, you may be kicked out of your apartment because you planned that I'm gonna use that $500 to pay for my rent, right? Yes, they did not say. So they were very, very hush hush about that. Now, knowing ACM, because 30 years ago I went to an ACM organized programming contest, which is not a codeathon, but I would suspect it is similar. It is not open ended. In other words, they just go. They do not just tell you do something to impress us. Okay, which is basically what hackathon was in SF Hacks. So I think this one is going to be a lot more specific. So they would probably give you a very well-defined problem to solve. So whether a solution works or not is not going to be. It's kind of subjective. I think this is good. Okay, I think it's going to be very black and white. They will be very well defined whether a solution works or not. And there might be multiple problems to solve instead of just give us one project. Okay, and I think it will be something that you normally do not see in a textbook. So it's not going to be an algorithm that you can just kind of plug in from a textbook and say, problem solved. Okay. So I think this is going to be one of those, competitions instead of a typical hackathon, which is just kind of like, okay, do something to impress me. If you impress me, I might hire you kind of thing. This one is more like, let's see who is the better programmer. Yep. So it's similar in a debugging bee in the sense that the problem is well defined, but it is not going to be the same in the sense that you're not given a broken program to fix. So you'll be given a problem to solve. And I suspect it might have limitations to a certain extent of what programming language you can and cannot use. I don't think that's going to be a big deal. I think they would just have a long list of programming languages. C, C++, Java would definitely be one on the list. But if you look at the flyer itself, it's written in JavaScript. So that's a pretty big giveaway that JavaScript will also be one of the programming languages that you can use. So the thing about JavaScript is you have to understand what is available as libraries and modules that you can install. Okay, because if you know those modules and that you can install, you can simplify your own code by a great deal if you know what you can install in JavaScript. Okay, and also data structures that are already well supported in JavaScript. So that's going to be helpful as well. So, are there any questions about this? No questions? Well, that kind of brings us to something that will bridge to our lecture today. So, I like the enthusiasm. Okay, so JavaScript does have an idea of a set, okay, which is something that we have been talking about since the beginning of the semester. So when you look at the JavaScript set prototype, it has some of the things that we want, but it doesn't have everything that we want. So I'll just kind of go through this very quickly, because I know not too many people in this class, want to program in JavaScript because it doesn't really align with your transfer classes. But on the other hand, JavaScript is a very practical programming language that many employers do look for. So if you want to get a part-time job, in college to pay for some of your expenses, JavaScript is a pretty good programming language to pick up. So when you look at the methods, it has got add, which is basically just to add an element to a set. Okay. So it's just unioning with a singleton set with whatever element you want to add. Clear is to clear all elements from a set, so it would turn a set into an empty set. Okay. It can delete a single element from a set, which means if it is found, it is going to be removed But if it is not found, nothing is being done to the set. You can look at all the entries. So this returns an iterator if you have, well, okay, wait a second. Hold on a second here. 400 is the prerequisite of 430, which is the prerequisite of this class. So you guys should have been exposed to the concept of an iterator already. Okay, so this function or this method returns an iterator, so which in return allows you to go through every item in a set, okay, which is kind of handy. But you can also use for each as a function, as a method. So this is where the programming languages start to differ, because in older style programming languages like PHP or Perl and stuff like that, for each is a control structure, it's like a loop, okay? But in later or more modern scripting programming languages, for each is actually a method of a set. So you basically say, this is an object, which is a set dot for each. And then what you pass to for each is a function. So, and the function in JavaScript can be anonymous, which means it doesn't need to have a name. And you just apply the code to process each element as a parameter to this method for each. So this is yet another way to go through all the elements in a set to perform some operation. Has is basically the same thing as the element of symbol. In our class, it returns true if the element is a part of the set, and it returns false if it is not the case. And then values is basically just returning an iterator object, which is going through all the values. It is really about the same as entries. It doesn't make a whole lot of difference. The only reason why they have both entries and values is because in JavaScript, they also have a map class, MAP map class, which has a lot of the same functionality as a set, except in the case of a map, it is more of a key value pair where you can associate a value on a particular key. And it has this operator. The initial value of the at iterator property is the same function object as the initial value of the values property. Okay, so it seems like everything is done for you, but there's one huge caveat to the implementation of a set in JavaScript. How does it check whether things are the same or not? Well, yep. Nope, you do not. So the value equality is checked using the triple equal operator. And if you do not know JavaScript, the triple equality operator checks for the type first. If two things are of different types, they're automatically different. If they're of the same type, then it checks the value. So it doesn't allow automatic type casting to check for equality. Okay? But the way you compare a set with another set, it doesn't work properly. The objects are of the same type, but then it doesn't know how to define equality between two objects. So it can work across your strings, numerical values, booleans, and stuff like that, but it does not work on objects. Which means if you want to implement a set that contains another set as an element, this is not going to work. So you will have to kind of extend it to get it to work, where you can have a set of a set of a set. You can have nested your sets. The other thing that it also does not work with are tuples. So the concept of a tuple in this class is basically the same thing as the concept of a list or an array in most programming languages. JavaScript does have the concept of a list, /array, okay? But the equality or the checking of equality does not check for that either. So you cannot ask, is this array triple equal to that array? Even if all the elements are exactly the same, it will say they're not the same, because the reference to those two different objects are different. Okay, so that's why this gets you started, but it only gets you up to a certain point. If you want to implement the concept of a set the way that we talk about it in this class, you will need to extend the methods in order to check for equality, containment, and other things too. Okay, So I'm going to leave it at that, because we do not yet have a homework assignment that requires the use of a set concept, but we will. So this is a little preview of, you might want to look into the implementation of a set. Not necessarily using this in JavaScript. If you don't want to learn a new programming language, you can probably do it in C and C++ as well. But this is a preview of what we'll be talking about. All right, so getting back to the content of this class, the homework assignment is due about 16, 17 minutes ago. So we can now talk about the solution of that. Oh, this is the wrong class. It's interesting how some topics, some content is moved between 440 and 310. So there's some stuff from the original 440, that got moved into 310 and vice versa. So these two classes, got some exchange of content. All right, so getting down to here. Okay, so CNF is what we're working with today. This is your new homework assignment. It's called Resolution and Proof by Contradiction. I got the due date all set up, which is 1 week from today. And then we're going to talk about the solution or the answer of the CNF homework assignment that was due today. All right, so this is what it looks like. And I'm going to use a text editor to show the derivation. Now, there's no one single way to get to the CNF, so there can be multiple ways to do it. So do you guys want me to kind of go over this, or do you guys think like, okay, I got this, okay, let's just move on to something else? Go over this? Okay, all right, so we'll go over that. So we have a negation of P or Q implies R, and then the OR, and then another negation, and then inside we have Q and S or not T. So this is the notation that I choose to use because it is easy to type using just a text editor, and also to computer engineers and electrical engineers, that's how they use most of these symbols. They do not really use the exclamation point to mean negation. Usually they use a slash to mean negation, but the use of an exclamation point should be familiar to you because that's what C uses as a Boolean negation. Is that okay? So are we good with the notation first? Okay. So the first thing we need to do is to get rid of the implication. So the implication is turned into the negation of the first part. Okay, so P or Q as a whole thing needs to be negated, and it has to be ORed with the second thing. So that's my only change, is to replace the implication. Okay, this is using implication definition. Okay, all right. So once we have that, then it's really a matter of applying one of those two rules. Okay, distribution and De Morgan's law. De Morgan's law is how you can move a negation on the outside all the way to the inside until it applies to variables or constants. So that's why we need De Morgan's law. Distribution, on the other hand, is what you need to use in order to convert nested things that you do not want to use into nested things that you do want to use. Okay. So we can apply De Morgan's law first. Okay, so we'll apply De Morgan's law to the negation of P or Q. So we'll handle this part first. So De Morgan's law says this whole thing just becomes not P and not Q. Okay, and then the OR R is outside of it, so we have to kind of nest our parentheses carefully in this case. Do we have any questions about this step, this particular application of De Morgan's law? No questions? So we are okay here? All right. So we can apply De Morgan's law again on the other side. And on this side, we have a negation, which is this negation symbol here. It is applied to the implicit conjunction, which we represent as multiplication here. So we can apply De Morgan's law here too. So it becomes the negation of Q, the negation of the first item, or the negation of the second item. But when you write the negation of the second item, you have to remember to use parentheses, because the negation is not only applied to S, it is applied to S or not T. So the entire thing, S or not T, is negated like that. Are we still good so far? Okay, so I'm going to write here and say, this is an two applications of De Morgan's law. Okay, all right, moving on to the next one. Looks like we can still apply more De Morgan's law, right? Because we got this negation here that we can apply De Morgan's law, and then we got this negation where we can apply De Morgan's law. So that's what we're going to do. The first negation, this one, is applied to the or here. So what we end up with here is the negation of not P, not Q, not P and not Q, and then the whole thing ended with not R. Sorry? And not R, right. So that becomes the first term. And then the second one, we have not Q all by itself, and then we apply De Morgan's law to the other part. So this negation is distributed to not S and not T, not T, but then they will be connected by a conjunction. So now it is important to put the parentheses around the entire thing, because we end up with not S and not T. So I'm not even bothering to do the simplification at this point. So once again, we have two applications of De Morgan's law. In this case, over here, we can apply De Morgan's law again, because we have the negation of an and. So this becomes not P or not Q, and then the entire thing and not R. And then the other side, I just do one single simplification, which is not Q or, and then this is not S and T. So this time we have one De Morgan's law application, and we also have one simplification. Are we doing okay so far? Okay. All right. So we take a look at this and go, are we close? We can do another simplification. So let's simplify first, because not P is just P, not Q is just Q. So we have P or Q, the whole thing, and not R, or not Q or not S and T. Okay, so this has 1x of simplification. All right, so now we look at this expression and go like, it looks like we can't apply De Morgan's law any further. Okay, we have pushed the negations all the way down to individual variables. So now what can we do? Well, first of all, you ask the question, is it in CNF? Because if it's already in CNF, we're done and we don't have to do a single thing. But it's not, okay? It's not in the CNF because the telltale sign is the last operation we need to perform is an OR. If it were in CNF, the last operation we want to perform is an AND, okay? And then the other thing is we also have like a conjunction, which is this thing here, applied to a disjunction, okay, as a component, and then we apply disjunction on top of that. So it's not really organized the way that we want it. All right, so that means we need to do some work here. So the first thing we can do is to do a distribution. So we'll deal with this side first. So once you distribute this, it becomes P and not R, or let's see, Q and not R, like so. Okay, and then we have another OR here, not Q, and then we have another thing here, which is or not S and T, like so. So this is after 1x of distribution. And the other part is really just the dissolving of the parentheses. So are we good so far? If the question is asking for a DNF, which stands for disjunctive normal form, we are done. But we are not. We want CNF, conjunctive normal form. So, okay, what do we need to do now? Well, you can do some simplifications first. Okay, so my advice is to simplify as frequently as you can, and then because then you end up with a smaller thing to work with. So the question is, well, can we simplify here? Nope, nope, we cannot simplify because we do not have terms that contains another term. So there's no term within the disjunction that implies another term within the same disjunction. So we cannot really apply simplification. All right. But distribution doesn't, there's no distribution rule that says, we can expand, something like this magnitude. So what are we going to do? Okay, so you can look at this entire thing just as one thing. Okay, then you can apply distribution. Okay, so I'm going to do this like, maybe just a few times, then we'll just go for the quick way to look at this. Okay. Yep. Say that one more time. Oh, use a bigger font. Okay, sure. Yeah, go ahead.
Isn't there something called double distribution?
You can double, triple, quadruple, because the operations can nest.
Where you have Q not R
Mm-hmm.
or Q not R, you can make that into a like P or Q and then P or not R and Q or not R and not R and not R, right? On the left hand side.
Say that one more time.
If you look at the P not R,
Uh-huh.
Q not R,
Yes.
then can't you double distribute that as P or Q and P or
Yeah.
not R?
Yep. You can do that. But I'm doing it, really one step at a time. So I'm only applying the rules that we have already been introduced to, but only one part at a time. So if I do this, okay, and okay, let me just kind of simplify this a little bit. I look at this entire thing as uppercase A, okay. So now it becomes P or A and not R or A. Do we agree on this? Okay, because that's one of the basic distribution rules, okay, that we have talked about. So now we look at this and go like, oh, but wait, A is a complicated thing. It by itself is a big disjunction. So we copy and paste it here, and then we copy and paste it here. Okay, now this is progress, okay? Even though it looks really ugly, it is progress. It is progress because if I can turn this one into a CNF, if I can turn the other one into a CNF, then the conjunction of those two is a CNF. So I have just reduced my problem to only have to deal with one side and say, okay, I want to turn this into a CNF. Okay, and it's closer to a CNF now than before, because before there was one more conjunction in it. So what we do now is we apply the same technique. So we look at the first term, okay, we'll keep the second term exactly the same it is for now. Okay, well, we'll get to there when we get to there. So we look at this term and go like, how do we turn this into a CNF? You basically have to kind of look at this and say, we got a conjunction that is inside the disjunction. We don't want that, right? So the way we look at this is to say, okay, we have a conjunction within a huge disjunction. So we group the rest of the terms together. So we group all of those together, and we'll just kind of ignore this side and say that we are not working with that side just yet. And then this time, we look at all of these things as A again, okay? If you don't mind me reusing A, we can use B if you want, So we look at all of these as B, then we can apply the distribution rule. So we end up with Q or B and not R or B. Are we okay so far? Do you guys see how I'm doing this like one level at a time? Okay. So what is B? Well, unfortunately, B is not a simple thing, but that's okay. Okay, we just stick B, down here, and then we stick B down here. are we closer to a CNF? We are definitely getting closer and closer, because when you look at the original one, it has got all kinds of stuff in it that does not fit into a CNF format. But now, hey, we only got one more thing left that does not fit. But we can simplify as well. Because even at this point, you can see that the first one, it has got Q, not Q, both as components inside the disjunction. Then you just say, hey, Q or not Q is true. And then true or whatever is true. You cannot turn something from true to not true using disjunction. So that means, oh, okay, we can get rid of this. This whole thing is simplified to just true, but true and whatever is just true. Well, excuse me, true and whatever is just whatever. So it gets simplified entirely out of the whole thing. Is that okay? And then we look at this term here and go like, can we simplify this one? No, we have to distribute. We cannot simplify, but we can distribute, right? So we look at this thing and say, okay, we have to distribute it. So before we distribute, I'm going to do the same thing just to be consistent and with the technique that we have used before. So I'm going to leave the other side the same way as it is for now, because I just want to deal with one side at a time. So now we look at this and go like, oh, this is a conjunction or something. What something are we talking about? This something. I look at that whole thing as C. So now I can say, okay, if I define C this way, it becomes not as NT or C. And then the rest of the expression stays the same. But then we look at this and go like, oh, we can apply distribution because we have a conjunction on one side and then we are applying a disjunction on the outside. So now this whole thing becomes not as or C and T or C. And then of course the rest are the same as they are. Okay, so we keep them here. And then look at this and go like, well, what is C? Let's go ahead and look at C. C is not R or P or not Q. Okay, fine. Copy and paste it. Stash it here. Stash it here. Oh, we are done with one side of the equation. Now, can we do some simplifications? Maybe, maybe not. Okay, we have to look at the other side first. But at this point, there's no simplification that we can do with these two, because we are not seeing two terms of the same, and one does not imply the other either. So there's no simplification we can do right now at this point. So now we do the same trick on the other side. In other words, now we turn our focus to this part here. Okay? Is this way longer than yours? Well, but I am breaking it down into very simple steps. In other words, when I apply the rule of distribution, I'm only distributing one thing at a time. I'm not doing double distribution or triple distribution, which can be done, okay? But this way, it's really, really step by step, and the chances of making a mistake is lower. Which is one of the biggest problem of this question is, you can just have one, stupid error, and then it just impacts, the whole thing. So in this case, I'm going to do the same trick here, and just make it, really, really, really step by step. So with this, we will, say, let's look at this part as D. So this entire thing is D, and so we can now expand this and say we got Q or D, and then we have and, not R or D. But what is D? Well, D is not simple, but it's just a matter of replacing that and here and here. So are we good so far? And let's see, can we simplify? Oh yeah, we can simplify because we have Q, not Q in one disjunction, and because the disjunction is inside the conjunction, so that means this entire thing is simplified out. Okay, cool. And then here, we can also simplify because we have not R or not R, which is just not R. Okay, so we can simplify the whole thing and just take out one not R. And now we have this. Well, at this point, we can do another trick like what we did before. Okay, control. So we reorganize things a little bit so that it looks like it is in the format that we can apply distribution. So I'm just gonna move this one over here and then get rid of this plus. And then we now look at this entire part as E. Okay. And so we can apply distribution to only that part. Okay. So this whole thing now becomes not S or E and T or E. And what is E? Well, E is fairly simple now. So we just put it here and put it here. So technically speaking, we have our CNF. This is CNF because when you look at the lowest level of the parentheses, each one is a disjunction only involving either variables or the negation of a variable. And then when you look at the overall operation, those are all connected by a conjunction. So it is already in CNF. But we want to look at the possibility of simplification. Yes.
Excuse me, because I'm bachelor in electronics.
Uh-huh.
So I remember in logic, in max term expression
Uh-huh.
like this, we should have, as example, in right side on this case, we should have T on first one, two. This means 4 letter exactly for each expression. This is to normalize the.
We are not doing normalization. So we are not
It's kind of that. Right now it's the max term.
max term. We are not doing max term.
It's max
Well, to us, it is called a CNF.
CNF. Yeah.
Conjunctive normal form, which is already in conjunctive normal form, but it can be simplified. So I would like you guys to look at, okay, let me just label it so that you guys can see which one I want you to look at. This is E, this is F, okay? And G is over here. So just look at F and G and tell me, do you think they are related? Okay, so G has not R, the other one has not R. G has T, the other one has T. G has not Q, the other one has not Q. Oh, but the other one also has P. In other words, one is more restrictive than the other one. So which one is implying which one? In terms of implication, does F imply G or does G implies F? F implies G. Okay, very good. In other words, if F is true, G has to be true. Okay, all right. And both of these terms are inside a conjunction, which means we are things are getting more and more restrictive. So now I want to ask you, which one do you think we can throw out and it does not really impact the rest of the expression, doesn't impact the value of the expression? G can be simplified out. Very good. Okay. So we throw out the term G. Okay. So now we have a simpler expression. So we got this one. We have F. We have to keep F because it is the more restrictive one between F and G. So we have to keep that. And then we got this. Okay. Yeah, we will get to it. I know some of you are looking at that and go already, hey, but we can do that. Yes, we can. So now we focus on H, I, J. Okay, I don't want to use I, so let's call it J. So when you look at these two, okay, again, one has not S, both of them have not S, both of them have not R, both of them have not Q. One has the extra term of P. Which one can be thrown away? J is the one that we can throw away, so let's do that. So we get rid of that, and that becomes the final CNF for this particular question. Are we okay so far with the whole process? Maybe? Okay, so let's just say that you are doing your homework assignment, you get to a certain expression and you think, okay, this is what I'm getting, after deriving the whole thing. How do you double check? How do you know that the expression that you end up with is in fact correct, that it expresses exactly the same thing as the original expression? You can do a truth table. Very good. So how many items do we have in the truth table? How many rows? Yep. So we got how many variables? We got P, Q, R, S, T. We got 5 variables. So that means we have 2 to the power of 5, which is 32 rows in the truth table. Doing it by hand is not going to be useful because just as you can make a mistake during the derivation, you can also make a mistake when you work by hand to make the truth table. So the way to do this is not to do it by hand, but to use, you can use a program, but writing a program just to do this may be more work than it's worth. A spreadsheet. Okay? You can use a spreadsheet to do this. Okay? So let's check out. Do you guys want to check out how to use a spreadsheet to do this? Or do you think like, oh, please, no more spreadsheets in this class? Okay. I mean, the next calculator, the TI releases is probably just a gigantic spreadsheet. Because it makes sense, right? So let's go to, I'm just thinking about using a built-in one or using Google Spreadsheet. I will just use a built-in one. We can always upload it later. Okay. So the way I'm going to do this is I'm just going to use a number first, okay, as a seed, and where we'll get something out of it. So this is just n. I'll call the number n for no particular reason. And this row is whatever the previous row has plus 1. And I'll just make 31 of these things. So I have to work out to row 30, 32, 33, okay, because I need 32 items. Okay, so I got 0 to 31. Why do you think 31 is an interesting number when we have 5 variables? 2 to the power of 5 is 32. But why do we end with 31? Because we started with 0. Okay. So now you have to think about base conversion. With a 5-bit number, I can represent every unsigned value between 0 and 31. Right? They go from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. Wait. If we say that a 1 is true and a 0 is a false, then we have all the values for all the 5 variables in this case. Okay, so the next question is to say, how do we work this out? We got P, Q, R, S, T. So how do we know the value of P versus the value of Q versus the value of R and so on? Well, okay, now we have a decision to make. So the decision we have to make is to say, do you want P to be just the one alternating between true and false? So it's true, false, true, false, true, false, like that. And then T being the one that has 16 rows of true and 16 rows of false. Or do you want the other way around, where P is the one that has 16 rows of true and then 16 rows of false, and then T is the one that just alternates between true and false? That's one decision that we have to make. Which one do you want to do? The second one, which is T alternates. Okay, so we want T to alternate. All right. So the idea here is if you want this table to be truly scalable, which means, I can add another column easily and make it work, then you wanted to do it the other way, which is to make P the one alternate. But since we have chosen to have t alternate, we can do it that way too. It's just a little bit less scalable because you can't easily just add a column. Yep.
Couldn't you just copy the entire thing to the one?
I'm just going to use math to work this out. Okay. Hmm?
Scale it.
Yeah, to add another column, you have this. So first of all, n has to be scaled, but that's easy because you just expand it. You just copy and paste the 32 rows. But then the columns, I can make it scalable as well. I can just make a new variable and just block copy a whole column over to the other one, and I can make that work. Yeah, with this one, it's a little bit harder because there's no, I cannot make an assumption of how many bits we're dealing with. There's no implicit number of bits that I can use in this case. So, but it will still work. Okay. So the way this works is we have to use the mod operator. This one is easy because all we are doing. Okay, let me make this bigger. Okay, because I need to refer to the first column. So all we're doing is to say, let's take n and mod it with 2. Then it'll just alternate, right? Are we doing okay so far?
Yeah.
Because anything divided by 2 is either a 0, either has 0 or 1 as a remainder. And then because n is just a sequence of numbers, so that means t is going to alternate between zeros and ones. Okay. Pretty cool. So now the question is, what about s? Okay, we also wanted to kind of alternate, except it is true, true, false, false, true, true, false, false, true, true, false, false, and so on. So how do we make that happen? What about this? We do a mod again, okay? But this time it is the mod of the floor of n, n divided by, okay, got it. Forgot to put an equal first. That's why it's not recognizing it as an equation or formula. So it is the floor of n divided by 2, the whole thing mod 2. Is that going to work? Well, I'm pretty sure it's going to work, but then, yeah. And we just do the whole thing here. And what do you think the next column is going to look like? Oops. Huh? Yep. So now I'm going to get a little bit lazy. So I turn the A into a $sign. So it doesn't change when I copy it to the other columns. Okay. And with this one, it is going to be divided by 4. And by the way, there is a way to know, which row or which column and also which row this cell is in. So I could have used that to automatically calculate what power of 2 am I dividing n with by. Okay. But I'm just not doing that. This is the reason why if I want it to be truly scalable, making p the one that just alternates is going to be really cool because I can use the column number -1 as the power of 2 to divide. So now I can just just massively copy the whole thing and it will just work. Okay, so I might as well just work with the other ones too. Just copy over here and also here. So with this one, we got division by 4 already. So we need to divide this one by 8. Okay, let me just double check. Did I change the right one? Yep. And this one is going to be divided by 16, which makes sense, right? Because, the range of n is going from 0 to 31. So for the first 16 entries, n divided by 16 is going to have a value of 0 once you take the floor, right? And then the second half is going to have a 1 as the result of the division after you take the floor. So actually it does make sense, just mathematically. Okay, and then we just copy and paste the whole thing. Well, right, seems to work. So are we good so far? Okay. So now we take a look at this, and we have all the independent variables done. So now we have to enter that equation. So we go back to here. There's no easy way to translate that, as far as I know. So, so with this one, you pretty much have to just kind of hand enter the equations. So it becomes the negation of not the OR of P and Q. Okay, so we have P, Q, and then we close the knot, and then we have the OR of with R, which is this one, and that takes care of the first negation. And then the two items are connected by an OR, by an outer OR. And then the second item of the outermost OR is the negation of an AND in the inside. And then the first component of the AND is just Q by itself. And then the second item of the AND is a OR operation involving S and the negation of T. Okay, close, close. I have no idea where I am in the nesting of the parentheses. Am I missing an OR? This P or Q? Huh? With the R? This is the R. Yeah, so the R is ORed, after we perform the negation to. Oh, okay, I see what you mean. So we are missing an OR. You're right. Okay, so as it is right now, this is it is now as a part of the knot. Okay. So we have to put an OR here. And this becomes the second value of the OR. And then we have to close the first knot right here. And then this is knot, and this is a part of the outermost OR. Okay, so that's good so far. This is the last parentheses, I think. Okay. Looks good. All right, so you have a truth table like this. You can do some spot checks, if you want to, just kind of plug in the values and do it by hand. And now we have to plug in the other one, which is the CNF version of the whole thing. So let's go ahead and do that. This is why I do not like prefix. Prefix notation requires a lot of counting of parentheses, which I really do not like. Huh? Yeah. So now we need to enter this one. Okay, this one is actually a lot easier to enter, by the way. So we'll put it here, and this becomes the OR of a whole bunch of things. Okay, I'm going to use the same order here. So we'll be dealing with the knot of S, the knot of R. I should have written a parser so it can automatically convert between the two equation formats, right? And then we have P by itself, and then we have the negation of Q, like that. Close, and then let's see. This is the first OR. Okay, that's good. Okay, so we need another AND. Okay, we need an AND on top of this. And then we specify the second component of the AND, which is by itself an OR. And then we got T, which is this one. We got the negation of R. We got P by itself. And then the negation of Q. Close, close, close. There we go. All right, so this is the moment of truth. No pun intended. Okay, so, oh no, it's not working. The last few items are not working. Okay, so that really kind of giving me an idea of where the mistake might have been, because the expression that I end up with is has more items that are true than the original item. So when the original item is false, the new equation is true. So that means it is not as restrictive as the original one. So I made a mistake somewhere. But at least I caught it before I turned it in. Okay, so we have to go back to the derivation and find out where the mistake is. Yes, but I didn't get started until now. Okay. Okay, so we got these items, where one is false and the other one is true. Okay, but the other ones worked okay. So we already know that if something is true in the first one, the second one is going to be true. It's just that if the first one is false, some of the items in the second one is going to be also true, which is not what we want.
I got the same thing, but with no P at the end.
Huh?
I got the same thing as you, but no P's at the end.
No,
Yeah.
no P. You mean this one?
Yeah.
Yeah, we simplified out the P's.
Okay.
Yeah, if you go to your A thing,
On which line?
I use the P, not R, Q, not R, and Q and as in one thing, and then simplify that into the not S or T.
Yep.
If you go to line 7,
Uh-huh.
for the Q not R,
Mm-hmm.
there's already a not Q, then the Q is kind of irrelevant, so you can get rid of that.
So are you talking about the relation between this Q
Yeah.
and this not Q here?
No, in line 7, if you look, since you have a or not Q, then where you have the Q not R, the Q is kind of irrelevant because if it's a not Q, then that's already going to give it a true.
Oh, I see. No, he's not talking about resolution. He's talking about these two terms. Okay, because we have 4 terms in the or basically in this case. We got one term, one term, one term, and one more term in a big disjunction. So when you're talking about big disjunction, it is looking for the more general case. Okay, so the more specific case does not need to be here. So this one can be simplified out already at this point. Is that what you're talking about?
Yeah, and then you could use the same logic to take the P out of the not R.
On the left.
You're on about that.
On the what?
You mean on the left?
Yeah.
Okay. It's like the left part of the big disjunction.
You mean this one?
Well, okay, sorry. Pull it like that.
Okay, so let's work from here. So if I work from here, then we have P or not Q or not ST on one, and then we have not R or not Q or not ST on the other one. And then we expand this one. It becomes not S or P or not Q, T or not P or P or not Q, and then we expand this one too. So this time I'm kind of merging all the expansion into one. So this is not S or not R or not Q, or T or not R or not Q. Okay, so, sorry?
The very last one should be N.
Should be end.
Yeah, NT.
Oh, right, so this is ended right there. And this is not gonna. Okay, so now we have to cross between these two. Uh-huh.
I remember last time you talking about generalization,
Mm-hmm.
simplification.
Yep.
So at the very end, shouldn't you keep the shorter term based on your solution
Uh-huh.
at the very end?
Okay, so based on the original derivation. Uh-huh.
Last time you told us if you have A or B and A or B or C,
Uh-huh.
it will be equivalent to A or B.
Okay, let me think about this. We can get rid of the more general term. So we keep the more specific term. You're right. Okay. There we go. Okay. So yeah, good point. So we we got rid of the wrong one. Yep, that's right. Okay, so we did everything right up to here, except we got rid of the wrong one, because in a disjunction you can get rid of the more general terms, because the more specific term really defines the actual result, right? So I got rid of the one that has fewer ors, but it's actually the one with a larger or that we should be getting rid of, because that is the more general term. So you're right. Very good. Okay, good job. Yep.
Is it still F implies G?
Huh?
Is it still F implies G or is it G implies F? Is
The implication is G implies F.
instead of F implies G?
Correct.
Instead of,
Yep. So I got that part reversed. Okay. So we only keep not S or not R or not Q. And then we have T or not R or not Q. Sorry? This is the more restrictive one, which is what we want. The result, okay, so the way that the truth table is not matching is because we ended up with a more general expression. And that's why we have more columns of truths or more rows of truths than there should be. So this will change that. Okay, because what we did here is we got rid of P from both of them. So if we go back to the spreadsheet, okay, this is easy to check though, because now we just, we first edit the labeling. So we get rid of P here, and we get rid of P here. And then we go to the expression. P is column B. So all the references to column B should be removed. So get rid of this column B, and then we get rid of this column B here. Okay. And then we just copy this all the way to the end. And this time we should have all matches. Yeah. So good job. So he caught my mistake of because I flipped which term is more general, so I got rid of the wrong term, and that's why the truth table worked out the way it did. But this is the truth table now. Okay. So did everybody catch my mistake?
Yes.
Okay. Very good. So that's another way to teach a class, is to make a mistake, and then say, "Oh man, I made a mistake, but you guys caught it."
You were testing us.
Yeah. Well, I mean, that was a good problem solving session. So good job. Cool. So I was already suspecting, because I know what the answer is supposed to be. It only has like 3 items, and go like, how come it has 4 items? So so that's why. But it is also, we can also tell why that is the case, because with these 3, which were originally false, because P is true here, that turned it into true. And then because P is true here, that turned into true. And because P is true here, that also turns it into true. So it can be explained that way as well. But finding the mistake is not quite the same. It's a little bit more difficult. Okay. So that's your homework assignment that's due today. So the ones that's due next week is based on this. So the one that is due next week is resolution and proof by contradiction. There we go. So in this homework assignment, see, I knew the answer already. Otherwise, I wouldn't have put it here. So the next phase is to prove a theorem using resolution and proof by contradiction. So there are 2 subproblems. The first subproblem is to propose T implies S and R as a theorem. Okay? So now you have to use proof by contradiction and resolution to tell me whether it is whether this is a theorem or not. And then the second proposed theorem is Q and R implies T. And then you also have to use proof by contradiction to show me whether this expression is a theorem or not. So remind me, what is proof by contradiction? What are the steps in proof by contradiction? Okay, so the actual mechanism of proof by contradiction is really just negating the theorem that you want to prove, and it with everything that you know, and then you want to get to a false. You want to get to a contradiction. Now, whether it's CNF or not is not specific to proof by contradiction. Okay, but we are using resolution as a mechanism to get to that false, hopefully. Okay, so that means you have to take each theorem, negate it first, then you turn the negated theorem into a CNF. Merge that CNF to this particular CNF, and then apply resolution. If you can apply resolution and eventually get to a false, which is a 0, then the theorem is true. The theorem is valid. Okay, it is a consequence of what is known to be true. If you get stuck, it's like, this is all the resolution I can do, but I cannot get to a contradiction. That means the theorem is not valid. It does not follow everything that is known to be true. So are we good with that? All right. You can look into the module itself. The module itself has 2 examples also. So you want to look into those and find out how to apply resolution and how to come to a conclusion of whether the proposed theorem is true or not. Well, is valid or not. So are we okay with this homework assignment? It's not quite as gnarly as the one that you just did. All right. So with this out of the way, we still got 10 minutes, so we can go back to counting. So when we get back to counting, there's a new homework assignment, on the horizon, in about a week or so. But before we get there, we'll finish the discussion first. So we are now in counting. We're still in counting. And the portion that we want to work with now is not really so much how many of something, okay? So this time, all of this discussion, okay, the pi notation, the exclamation point, permutation, and then combination, all of these has to do with counting, okay? It basically is just saying, okay, how many lotto tickets, how many unique lotto tickets can we have, given these are the rules, okay? So that's basically what we're doing, is just counting. But sometimes, in addition to counting, you might actually want to keep track of what are the actual permutations, what are the actual combinations. Why do we want to do that? Well, just the other day, I was over at the Design Hub, and several people were playing the Mastermind game. So the Mastermind game, which I also mentioned in this class, remember I kind of mentioned that in conjunction with cybersecurity when I mentioned WEP, Web Equivalent Protection, and how you can single out a single encryption key just by observing passively the traffic on Wi-Fi. Remember that? Okay. So that's a good example of, you might want to keep track of every single permutation, because you're basically saying, okay, this cannot be the one, this cannot be the one, this cannot be the one. You're eliminating possibilities within the set of all permutations. Okay? So this is why we want to look into this, which is to look into the permutation outcome set of an experiment without replacement. Okay? How do you generate that particular set? So let's look at the notations first. Okay, and I want to magnify this a little bit. There we go. So we are looking at TI as a trial. It is independent to all of the other trials, but it is without replacement. Okay, and we want to look at omega as a set of all of the outcomes of an experiment. there are m trials. So the letter that I choose to represent the number of trials is m, and that's used throughout the entire discussion. Okay. So what we want to know now is how do we generate that generate a set. So we want to use this notation to represent the outcome set of an experiment that has I trials, but the first trial has T as the initial trial outcomes. I'll give you an example. So let's say that you have 6 destinations, okay? I think last time we used the Bahamas, we used Lake Tahoe. Okay, let's do all the gambling places, okay? Las Vegas, Monte Carlo, Macau, and give me more. Reno. Okay, close enough. In 2 ways, it's close enough. Okay, so there we have 6 destinations. But I don't think the Bahamas allows gambling, but since we chose it already, we'll have those 6, right? So those 6 will now be in the set T. T has those 6 destinations. What we want to do is to say, how many trials do we have in this experiment? Let's say you can only choose 3 destinations for 1 year, okay, as your potential destinations. So I would now be 3. So we'll be looking at omega 3 of T. What it is going to give you would be a set of tuples, where each tuple is a 3 tuple. It has 3 items in it. And the 3 items will basically say which 3 possible destinations can you go when you have 6 possible destinations, order is important, and you only want to choose 3 out of the 6. So you might get, the Bahamas, Reno, and then Tahoe. Okay, you might, you might get, Macau, Reno, and then Tahoe, and so on. And order is important, so you can see, certain things having exactly the same 3 destinations, but ordered differently. Yep.
So, wait, did you say that T is the set of outcomes?
Right. So T is the available choices to the first trial.
Okay, so then you would plug in a T in the amount you want to choose, and you get out tuples that have that amount of items of T.
Correct.
Okay.
So I can give you an example. So we have omega 3 of just say ABC, okay? I don't feel like spelling out Monte Carlo all the time. So we'll just say ABC. So what this will give you would be ABC. Okay, you guys probably know what this is going to be. ACB. Okay, can you thank you. And then we have BAC, BCA, CAB, and CBA. Okay, does that explain what omega 3 is? It is the set of all possible outcomes, each one being a permutation, when we have an experiment that involves, in this case, we have 3 choices to begin with, and then we have also have 3 trials in each experiment. So is that okay? The 3 doesn't have to match the number of items in the set, so you can have omega 2, for instance. So you can have omega 2 of ABC, let's say, yeah, just do ABC because ABCD is going to be a little bit too big. Okay, so you can have AB, BA, AC, CA, and then you have BC and CB. Okay, so given 3 things to consider, but you only have to choose 2, how many permutations can you get out of that? That's omega 2 of ABC. Are we good so far? So now the question is, well, with a small number, we can kind of do it by hand, right? So now the question is, what if this is like relatively big? Like, if I want to ask you what is omega 6, okay? 6 being the subscript of A, B, C, D, E, F, G, H, I, J, K, H, I, J, K, like that. obviously this is going to be a rather big set of a whole bunch of tuples. In this case, they will be all be 6 tuples. But how do we generate that particular set? That is the question. What do you think? We have to use permutation, okay? But how do we generate that particular set?
We could draw the tree we did from last class and try and go down every path.
Yep, but if you do it by hand, it's going to be very cumbersome. So what we want to do is to have a programmatic way to do it. But before we get to the programmatic way to do it, I have a recursive definition that can generate it. So, so this is a permutation quote unquote generator. Okay, so the idea of a permutation generator is recursive. So the first one is omega 1. This part is not recursive. Omega 1 of a set is just the set itself. Does that make sense? So I give you A, B, C, D, E, okay? That's the set. And I say, we only got one trial in each experiment. What are the possible outcomes of the experiment? A, B, C, D, E. Okay? That seems to make sense. Yep.
Why isn't the set of elements and not like one element tuples?
They should be one element tuples. So are we good so far with that? Okay. So now the next question is, what if we are dealing with I, omega of I of t, and I is not 1, like 2, 3, 4, and so on? What do we do? Well, then we use this kind of awkward thing. So this is a union, which means whatever we produce for each term is unioned with whatever term we produce with the next one, and so on. So what are we producing? It's saying for each element of t, generate one term like this. Okay, so if t is A, B, C, D, E, then we have one term like this for A, one term like this for B, one term for C, one term for D, and then one term for E. What do we mean by that? Well, when E is A, then A goes here, A also goes here. So it becomes A as a set on its own, and then this is a cross product with omega I minus 1. So if this I is 3, then the next I becomes 2. Okay? But the set that you need to consider now cannot have A in it anymore because A has been chosen by this step. So that's why we have a T minus the set of E to consider when we perform the recursion. So that's how we recursively generate all permutations. So are we doing okay so far with this step here? We good? Okay. So if I can mathematically give you a equation, and which I call a permutation generator, how do you do this using a program? Yep.
I actually just wanted to double check. So the first instance you'll do omega 1, and then the next instance you'll go through every element of t and make the 2 tuples, and then the next one the 3 tuples, and generate permutations that way. Is that what's going on?
It's the other way around. So you start with this. So let's say I is 3 to begin with, and then t is A, B, C, D, E. So you start with omega 3 of A, B, C, D, E, and then each term here, so you have 5 bigger terms. So the one term is going to be the set of A, Cartesian product with omega 4 of B, C, D, E as the 4 elements. The second big term of the union is going to have B being here, omega 4 of A, C, D, E with B missing, and so on. And then you look at omega 4 of, let's say, B, C, D, E, and then you go back to the same definition. So it becomes omega 4 of B, C, D, E, and that in return becomes, for each term, which is B, C, D, E, so it becomes B here, omega 3 of C, D, E, and so on. Right, exactly. So once you have all these subterms, then you do a big union of all the terms that you have already computed, and then that becomes that particular omega. So we'll work this out on Monday, but if you guys cannot wait, okay? If you cannot wait, I'll give you a kind of ungraded assignment. I know you guys got a graded assignment already, But you can just kind of work this out, okay? Omega 2 of the set A, B, C, which we have already worked out by hand. But see if you can do this one using the recursive definition. Just kind of expand the terms, one by one. It's not going to take you a long time, okay? I guarantee you, okay? There are only so many terms you have to deal with. But see if you can work on this one, because that will really help you understand how that generator function works. All right, so I'm going to shut down everything and get ready to go downtown. Yes?